Good morning. Now, let's have a brief discussion about transmission lines. And regarding how many types of transmission lines are there and how to analyze each of the transmission line like that. So, this is the first part, and we are going to see some more parts regarding transmission lines. Fine. So, there are generally three kinds of transmission lines. Classification of transmission lines is into three types, and those classification is done based on the physical length of line. So the transmission lines classification is as shown. The first thing is short transmission line, and the second one is medium, and the third and the last is long transmission lines. Short transmission lines will have a length up to 80 kilometers. Fine. Then the medium transmission line will have a length between 80 kilometer to 250 kilometer. And for long transmission line, the length will be greater than 250 kilometers. In some textbooks, it will be like 80 to 160 and it will be greater than 160. You can follow as you wish. In some textbooks, it is given as less than 80 kilometer, and it is as 80 to 160 kilometer, and it is greater than 160 kilometer. So, it is written in some textbooks and it is written in some more textbooks. So, please see the options while you are filling, while you are solving a question, please check and solve accordingly. Right. Next, before going to sharp transmission line analysis, let's see some basic topic regarding that two-port parameters, two-port networks. And in this, for analyzing the transmission lines, we will be using ABCD parameters or transmission parameters. So we know the general format of ABCD parameters, general equations. Those are Vs equal to AVR plus BIR. This is one equation, and the other equation is Is equal to CVR plus DIR. You might be knowing this. A, B, C, D. This is the thing. Fine. For such kind of two-port parameter, the equations are as given. Now, let us see what is the no-load receiving event voltage. Fine. This is most important for analyzing the future things. This is the most important thing. Now, at no load, at no load, we know that receiving end current will be zero, right? Since load is not there, we can conclude that the receiving end current is zero. Therefore, upload. Please make the changes in the first equation. AVR plus B into zero. Now it becomes Vs equal to AVR. Therefore, we can write this as VR equal to Vs by A, right? But this receiving end voltage is with respect to no load. So, we can update this as VR naught. Okay, fine. Next. Now, one more thing. Is is equal to CVR plus D into IR, right? This is the second equation. Now, Is equal to CVR plus D into 0. Sending end current will be C into VR, right? This is no load receiving end voltage, right? So we will update it as VR naught. We already know, VR naught is C into Ps by A. Therefore, we can write this as Is equal to C by A into Ps. Fine. This can also be referred as charging current. In some cases, this can also be referred as charging current. Fine. Since it is on no load, so most of the current will be capacitive. So we can conclude this as charging current. Now let's analyze the short transmission line. The general representation of short line will be, this is Z, which is R plus JX. This is Vs and this is VR. IS, IR. This is the generalized representation of a short transmission line. Now, if we draw equations from it, we will be getting one C here, and we will apply KCL here. We will be getting Vs equal to, apply it, IR into Z or IS into Z, not an issue, plus VR, and IS equal to IR, right? Therefore, Vs equal to IR into Z plus VR and IS equal to IR. Compare these two equations with the standard T parameter equations. Vs equal to AVR plus BIR, and such the second equation is Is equal to CVR plus DIR. Fine. So now after comparing, we will be getting A is equal to 1, right? A equal to 1, B is equal to Z, C is equal to 0, D is equal to 1. So therefore, for a sharp transmission line, ABCD parameters will be 1, Z, 0, 1. This thing. This thing is very important. I mean, this is not so important for gate, but when we compare, when we use it for other AE exams, like many PSU exams are coming, for those exams this is very important. This is a straight question: what are the ABCD parameters for a sharp transmission line, and they will give the options. So please remember this thing, and once check it is symmetric or not. For symmetricity, for symmetry, condition is A should be equal to D, and it is proving, so it is symmetric. And it is reciprocal or not, please check it. For reciprocity, we have AD minus BC equal to 1. Once checked, it will be satisfying. Therefore, short transmission line is both symmetric as well as reciprocal. Fine. Now let's draw a vector diagram corresponding to short transmission line. Fine. Generally, we can draw vector diagram in two ways, but I am using the easiest way possible. Let me take the reference as receiving end voltage. Let me take the reference as receiving end voltage. And now IR will be lagging or leading. Please check. IR will be lagging or leading. Since we are using an inductive load, the transmission line is filled with only resistance as well as inductance. So we can conclude the current will be lagging, not appropriately 90 degrees, but it will be lagging. Somehow it will be lagging. So we can use the same line here also, right? The same parallel line can be used here also. And IR is done. Now, I mean, IR in the sense through this. And we need IXL also. That will be 90 degree. Fine. That will be 90 degree like this. IXL. Now, the equivalent and the resultant of this thing will be sending an voltage Vs. Now, if you want, you can see here also we can write it as Vs is equal to Vr plus IR plus IXL. You can see this thing. So again we can do this as I into R plus JXL. It is JXL because it is at 90 degrees now. So we should add as J. And VR plus I into, what is R plus JXL? It is again Z. Again we got the same equation. Right. So we got the same equation. This is the way of analyzing a short transmission line. And one more thing, since it since there is no capacitance involved in any of the thing, we can conclude this as charging current will be zero. Charging current, I mean through capacitor, because there is no capacitor here, zero. And this is used as a lumped circuit. We already discussed what is lumped and distributed networks in the earlier classes. So no need to go through that now. Please remember this as a lumped network. Short transmission line network is lumped network. And these are some of the important points corresponding to short transmission line. This is the way of analyzing a short transmission line. Fine. Now we have the next line is medium transmission line. Medium transmission line analysis can be done in four ways. The first one is receiving end condenser model. Second one is sending end condenser model. Third is nominal pi method. And fourth is nominal t method. Fine. Now, in this lecture, we will be seeing receiving end and sending end. In the next lecture, we will see nominal pi and nominal t. Okay. Now, before going to analyze these things, we have a small topic which is called Paranti effect. This is one of the most important effects of power system. This is most important effects of power system, especially transmission and distribution part. Now, what is Ferranti effect? At no load or lightly loaded conditions. I mean, load should be either zero or it should be lightly loaded. The magnitude of receiving end voltage will be greater than the magnitude of sending end voltage. The magnitude of receiving end voltage must be greater than the sending end voltage. Such condition is called Ferranti effect. This is generally not seen in short transmission line because this Ferranti effect is generally due to capacitance. But in short transmission line, since there is no capacitance, we can conclude that there is no effect of Ferranti in case of short transmission line. Or else you can analyze. Just write V R naught is, we know that V R naught equal to Vs by A. Therefore, Vs by what is A here? 1. So V R naught is exactly equal to Vs, but it is not greater or lesser. So we can conclude that there is no Ferranti effect. Fine. So this effect is due to capacitance present in the line. The main condition is during light load or no load conditions, magnitude of VR naught, I mean receiving end voltage, will be greater than magnitude of sending end voltage. This is called Ferranti effect, and this is the most important effect for analyzing the next transmission, I mean next methods. Fine. Let us see the methods now. First thing, receiving end model, receiving end capacitor model. Fine. Here we will be seeing R plus JXL. This is common. And here we will be getting a capacitor. Okay. For capacitor, we will be having, it is shunt capacitor, not series capacitor. So we will be having admittance. Okay. Please see this. And this is Z. We already know. This is Vs. And this is receiving end voltage VR. This is Is, sending end current. This is IC, charging current, and this is IR. Fine. Now let's start analyzing receiving end model. we here we can clearly see that is equal to exactly equal to IR plus IC, right? At this point, IS will be exactly equal to IR plus IC. This is simple basic KCL. Fine. And here we can write IC as IC can be written as VR into Y, right? Admittance into receiving and voltage. Fine. Now, IS can be written as IR plus IC. What is IC? VR into Y. Fine. Now, what is apply KVL here? Apply KVL here. If you apply KVL here, Vs will be equal to VR plus Is into Z. Fine. Vector IR into Is into Z. Therefore, what is Is here? Is here is IR plus VRY into Z. Therefore, VR plus IRZ plus VR into YZ. Therefore, VR into 1 plus YZ plus IR into Z. This is a representation. From here, we can conclude that after comparing with the general equation, we can conclude that A will be 1 plus YZ and B will be Z. And if you see clearly here, we can write the general equation here. CVR plus DIR. If you compare, then the remaining two equations will be, C and D will be Y and D will be equal to 1. If you see properly, these things will be appearing here. Fine. Therefore, ABCD parameters with receiving and model will be 1 plus YZ, Z, Y and 1. Okay. 1 plus YZ, Z, Y and 1. Now, let us analyze whether this effect has Ferranti effect or not. If you apply medium transmission line, if you analyze medium transmission line through this method, we can see Ferranti effect or not. Let's test. We generally know that VR naught is equal to Vs by A. Therefore, Vs by 1 plus Yz here. And many people will be feeling that since it is 1 plus something, so it is greater than 1. Therefore, we can conclude that VR naught will be less than Vs. Many people will be analyzing, but there is a thing here that let us ignore the resistance for some time. Let us ignore series resistance for some time. So if you ignore, it will be j omega L, R plus j omega L. Now I am ignoring resistance, and it will be j omega C, right? If you multiply these things, it will become j square omega square LC, and it becomes minus omega square LC, and therefore VR naught will be Vs by 1 minus omega square LC, and obviously the denominator will be less than 1 now. For sure it is going to be less than 1. Therefore, we can say that VR naught will be obviously greater than Vs. So we can conclude that this receiving end model will exhibit Ferranti effect. For sure it is going to exhibit, because there is a receiving, at the receiving end there is a capacitor. So we can conclude that there it exhibits Ferranti effect. And let us see it is symmetric or not. For symmetry, the condition is A should be equal to D, and here A and D are not equal, so it is not symmetric. Let's check for reciprocity. AD minus BC equal to 1. Now you use that 1 plus YZ into 1 minus YZ. If you use, it will be 1. So therefore reciprocal. It is reciprocal. Therefore, receiving in capacitor model is reciprocal but not symmetric. Right. So, and we can also see Ferranti effect here, and this is also one of the important point. ABCD parameters corresponding to receiving end model. These are the important points which are going to be asked in many PSU exams. Fine. Now, Let's analyze sending end capacitor model. Capacitor model. Now let me draw the circuit first. This is R plus JXL, or we take it as Z, and here it is saying that there should be a capacitor at the sending end. That is what I am adding now. This is VR, this is Vs, this is charging current IC, this is Y, this is Zn, and this is IR, and this is IS. Fine. Now apply KVL. Apply KVL here. It becomes Vs equal to VR plus IR into Z, right? Here it will be Vs na. So that's why I use it directly. Vs equal to VR plus IR into Z. And also Is. Once use Is equation. Is equal to IC plus IR, right? Here if you apply KCL, it becomes Is equal to IR plus IC. And therefore, now IC we already know. IC here is Y into Vs, right? Substitute that. Y into Vs plus IR, and IR plus Y into, what is Vs here? VR plus IR into Z. Therefore, IR plus YVR plus IR into YZ. Take IR as common. 1 plus YZ plus Y into VR. Therefore, IR into 1 plus YZ plus VR into Y. This is Is equation. Now compare this equation with the standard equation. Is equal to CVR plus DIR, and compare this equation with the standard equation. Vs equal to AVR plus BIR, right? We got two equations and we are comparing these two equations with the standard equations. Now we will be getting A equal to 1, C, A equal to 1, B is equal to Z, sorry, C is equal to, what we are getting for C here? C, Y, and D is 1 plus YZ. These are ABCD parameters. We will write in a matrix form. It becomes 1 Z Y 1 plus YZ. Right. Done. Now let's check for Paranti effect. VR not equal to Vs by A, Vs by 1. Therefore, VR not is equal to Vs. Therefore, we can say that in sending end model there is no Paranti effect. We can assure this. Also, I am going to add one more point here. Here, VR not equal to Vs by A. We got this from here, right? We can say that if A is less than or equal to 1, first take less than 1, then VR naught will be Vs by some less than 1. So therefore VR naught will obviously be greater than Vs. At this point of time only we can see Ferrante effect. In any other conditions we are not going to see any Ferrante effect. If it is A equal to 1, we are not going to see any Ferrante effect, and if A is greater than 1 also, we are not going to see any Ferrante effect, and we are going to see Ferrante effect only when A is less than 1. This is the condition. Where am I? Here I am. Then C for symmetry. Symmetry condition is A equal to D, and here A is not equal to D, therefore we can say that this is not symmetry. And the second thing, reciprocity, reciprocal circuit or not, AD minus BC equal to 1. So A is 1, D is 1 plus YZ minus YZ. So it becomes 1 obviously. Therefore we can say that this is reciprocal. So receiving end model as well as sending end model, both are not symmetrical, but the circuit is reciprocal. It is not symmetric, but the circuit is reciprocal. We can clearly see that, because Here, if you come to short line, it is visibly also it is symmetric. It is symmetric in visual also. But here it is not where it is. Here it is not symmetric because if you cut this into half, we can see an extra capacitor here. Here also where this is. If you cut it exactly at half, we can see a capacitor at the sending end. So we can say that either sending end or receiving end capacitor model are not symmetric, but they are reciprocal. They are reciprocal, but they are not at all symmetric. And in receiving end model, we can see Ferranti effect, presence of Ferranti effect, but in sending end model, we cannot see any Ferranti effect. And in short lines, we can clearly see that there is no Ferranti effect. At any cost, there is no Ferranti effect. Fine. These are some of the important points corresponding to short lines and medium lines. And next, we can also conclude that medium lines are also lumped. This is also lumped parameter. Short line as well as medium are lumped. Only long lines are distributed networks. Now fine. We already saw what is lumped and distributed. No need to discuss this again. We don't want to divert our topic. We are in a discussion to prove whether this has symmetry. Ferranti effect or not. Whether the circuit is symmetry. Whether the circuit is reciprocal or not. These are the three conditions we are about to prove. And in the next class, we are going to see nominal pi and nominal t, and we are going to find whether those two methods have Ferranti effect or not. Okay, fine. Thank you. Thank you so much.